how long to diffuse across a bacterial cell. Meaning, if this is my cell, and now let's say I have some signal coming from the outside, and then it tells something, I know, the transporter or the whatever is sitting here, and now I have change in, could be phosphorylation of a protein or something else, and then this thing needs to move, let's say, from here until the other side or until the nucleus or whatever you have there. Okay, if bacteria, no nucleus. And let's give some options. Is it less than a microsecond? Or is it between microsecond and millisecond? Or between a millisecond and a second? Or between a second and a minute? Or between a minute and an hour? Question is clear? Okay, let's test our intuition. Who's voting for less than a microsecond? 1, 2. Who's voting for between microsecond and millisecond? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Who's voting between millisecond and a second? 2, 4, 5, 6, another 10. Between a second and a minute? 1, 2, 3, 4. Who's between a minute and an hour? 1, 2. Okay, a very pluralistic class. We have quite a range of answers. So what we need to do is to derive, to have an equation. For that, and for that, there's something called the diffusion equation, which I can throw at you. But just for the fun of it, let's see if we could derive it together. Okay, so let's take an analogy. Okay, because we're going to do something for diffusion happens in this thing called random walk. Who heard the term before? Okay, most people. But then the question is, what are the implications of random walk? So let's try to say, I'm interested to know in a given number of steps or a given duration in time, how far do I get? I'm looking for an equation that would connect those two. Okay, so the question of how far do you get, we could take like a real-life analogy, and that is, let's say I'm the particle that needs to diffuse, and I'm doing random walk. Random walk means that I walk this way, and then this way, and that way. And now let's say I need to get from here by 1, 2, 3, 4, 5, 6 steps. I'm reaching the cell boundary. And the question is, I guess here we have about 30 or 40 students. The question, if I was taking, so with 6 steps I could get there. The question is, with the random walk of, let's say, 30 or 40 steps, like the number of students here, would I be reaching it or not? Or how far would I reach? So let's try and do a simulation of that. Okay, so each one try to think if they're born on an odd or an even day of the month. Okay, and now let's see. Even. So even, let's say it's 1 step to here. Odd is here. Yeah, odd? We said odd is this way, yeah. Odd. Odd, wow.
Odd.
Even. Even? Even? Very strange class. Odd, we said this. Okay. So you see, actually, it's not very far from what you said. I didn't stay in place. I got somewhere. I feel my muscles. And we saw that I got some distance. And the question is, can we calculate what's the expected distance that I got to? It seems like I didn't get to 6 steps in the same direction, which is interesting. I didn't know to predict exactly how it would work. But actually, I did have a prediction, because I know what's going to come out in the equation. Okay? So let's try and see if we could derive it together. So this is me. Okay, in the first time, it's like coin flip or anything. I could either go a direction, let's call it A to here, or direction here, minus A. right? So this is a time 0. This is going to be time 1. I'd like to look at time 2, time 3, etc. So in time 1, I could be at either A or minus A. What are the probabilities? 50-50. So 1/2 to be here and minus 1/2 to be here. Okay. What about time 2? At time 2, I can already be at, I can either go here or here. So I'll be 1/4 of the time I'll be at 2A. 1/2 I'll be at 0. And 1/4 I'll be at 2A. Okay, this is 2 minus 2A, 2A. Okay, so far so good. Okay, I have a 0 chance of being here and here, right? Because it's whatever. Okay, let's do one extra step. So from here I could go to 3A. What is the chance for that? 1/8. Or I can go back to A. What is the chance to be here?
1/4.
So the chance coming from here to here is 1/8. But then there's also a chance of coming from here to here, which is 1/2 times 1/2, so 1/4. 1/4 plus 1/8, it's actually 3/8. Okay, that's fun. Believe me that it's already also true in this direction, right? It could also be here. So my chance of being at 3A minus 3A is also 1/8, and to be at minus A is 3/8. So far, so good? Okay, and you see it's symmetric, and it sums to 1. 1 plus 3 plus 3 plus 1 is 8 divided by 8. So all is good. Okay, so now what can I ask here in order to get an equation? So I'm interested what would be my location, right? So location is x. I can ask what's my average location. This symbol is like taking an average. So what's my average location? It's minus 1/2 times, 1/2 times minus A plus 1/2 times A, which is 0. And I could do it to the other things, 1/4 times minus 2A plus 1/4 times 2A plus being at 0 is again half. So you see, whatever I do, I'm getting 0, which is the point that was raised before. What's your name?
Eli.
So what Eli was saying, that actually I'm, on average, I'll stay in place. Okay, because I'm going to the left and right, same probability. So not so, I didn't get very far. After all this derivation, I got 0. So not a great equation. So what can I do?
Take the mean of the square.
Yeah, so I can think about the square or the deviation, the variance, things like that. Okay, it might sound familiar from physics, statistics, all sorts of things like that. So what you're curious to say, okay, let's do the same thing, but just at x squared. And the nice thing with x squared, it's always positive. So it's not very probable that I'll be left with 0 because I'm summing things that are necessarily 0 or positive. Okay, let's try and do that really quickly. So I have, if I was doing the same thing here, it's 1/2 times minus A, but now squared, plus 1/2 A squared. So that's A squared, 1/2, so it's A squared. Okay, that's my expectation for the distance squared. Okay, let's do the next one. 1/4 times minus 2A squared plus 1/4 times 2A squared. So that's 4A squared, 4A squared. 1/4, that's A squared. So this is 2A squared. Okay, A squared, 2A squared. Okay, let's do last one. 1/8 times minus 3A squared plus 3/8 minus 8 squared. And I have the same thing from the other side. What do I get here? That's 9A squared divided by 8 plus 3, it's 12. And then I have another 12, so I have 24 divided by 8 squared, which is 3/8 squared. And I want to continue this until I reach n steps. So what's going to be my equation? I can repeat this, but I think you're becoming tired. So it seems like it's 1, 2, 3. I think you can believe me, it's very probable I'll get na squared. And of course, we could do the math to do it properly, but in the spirit of this course, we're not taking all sorts of, we can calculate the Gaussians and do some derivations and stuff like that. But you can see that kind of like street fighting mathematics or equation derivation, you can see what happens in diffusion and what I'm getting. And I'm getting that the distance squared is equal to the number of steps times a squared.
This is one-dimensional diffusion.
You're right. But let's not confuse ourselves with one dimension versus a few dimensions, but it's not very different. Okay, let's finalize how do we get an equation. So what is this number of steps n? Can I write it differently? N is really number of steps. It's like the time that I'll be taking divided by total time divided by the time step. Okay, like it's how long does it take me to take a step times, this ratio is the number of steps. Okay, so now what do I get here? I have that the final distance is equal to a squared divided by delta t times tau. This is often denoted as r squared, the distance squared that I'll be taking. And what about this? What dictates how much a squared per unit time I'll be passing? Let's say now I'm going back to, let's say I'm a protein inside the cell. So there's all sorts of things that are going to happen here, like the size of the thing that is moving. Is it an ion or protein or something else? The temperature, what?
The density of the material.
Yeah, the density inside or the viscosity, all sorts of these names of things, how things move inside other things, hydrodynamics, etc. So I don't care about all these things. Actually, the physicists don't want to get into it so much as well. When you're writing the equation, you just take all of this and you call it d for diffusion coefficient. And you end up with the equation of r squared equals d tau. And this is the diffusion equation. And now we could take this and implement it in order to try and derive the answer to these questions. So maybe we want to change the equation, and instead of r squared being equal to d and tau, we're interested in knowing tau. So what is tau? Not so complicated. I just need to divide here. It's r squared divided by d. Because that's what we were asking there. You see the connection, what we're looking for? So what do we need to know? We need to know r and we need to know d. Do you know what r is? Let's say for the bacteria, 1 micrometer. Because I want to diffuse across the cell across the bacterium.
Radius or rate?
No, r here is the size. Okay, it was the rx squared, so it's the size squared. Okay, it's a bit confusing because r can sometimes denote rate and sometimes denote distance. I'm talking about like radius or length.
Okay, so
Maybe it would have been better to call it L squared or whatever. Okay, so you know what about d? How much is d? You already know the values in the course. It's about 10. But it's kind of a coincidence, but this is the case. D is about the diffusion constant, let's say for a protein inside the cell, is about 10. But then what are the units? The units are micrometers squared divided by second. That's another useful number to know, like the diffusion coefficient of things within cells. How do I know this is the units and that it makes sense? So just 1 second. So if, for example, I'm taking d, I'm plugging it here, I'm multiplying it by seconds, and then I'll get units of micrometers squared. which is again, it's the size that I'm looking for. So that fits well. We also look here. This is the units of this. So I have size of this, let's say micrometer square divided by micrometer square, and the second would go up, which is exactly what I'm looking for. So in terms of units, I'm okay. You would also see this stated sometimes not in these units, but let's say centimeters square per second. So and we could do the unit conversion, but I really like this, both because it's like small, nice numbers like 10, but also because micrometer square is the relevant time length scale. So you could work in what they call MKS units, like meters or centimeters, something like that. But actually there's something nicer in working in units. You just need to be consistent, which are relevant for the microscopic world. So micrometer is a good unit. But in the final equation, the way it's usually defined D, you actually have also a factor of 2 here for 1 dimension, or a factor of 4 for 2 dimensions, or a factor of 6 for 3 dimensions, which is not very intuitive. Maybe it is somewhat intuitive, because if you think about how far I'll get, the variance, it's kind of like you can think as independently I'm moving in this direction, and the random walk is also happening in this direction. And if I was able to jump, you could also think that. And then all of this is like, every dimension adds another factor and to the variance, and then it becomes 2, 4, 6. I don't know if that's very helpful. For the spirit of this course, we want to know kind of like the order of magnitude. You don't need to care so much, because a factor of 2 here or there would not change the result significantly, because I'm asking you, is it microsecond, millisecond, or millisecond there, or second to a minute? Okay, welcome back. Did anybody have an opportunity to try and update their estimate, or try and came up with something? Yeah, so okay, we could just plug it into the formula, right? Okay, so let's do tau bacteria. It will be roughly what?
1 to 10.
So R squared divided by D. So it's 1 micrometer squared divided by 10 micrometer squared per second.
0.1 second.
So it's about 0.1 second. So
20 milliseconds per second.
yeah, so we know that we're here. Okay, you see, by the way, that I'm not being very particular about whether it's 10 milliseconds or 100 milliseconds or something like that. And that relates to many things. There's this issue of whether it's 1 dimension, 2 dimensions, 3 dimensions. There's a mention, somebody was telling me about the fact when I was doing the derivation, it's not completely fair, because after you enter into the cell, you have the cell envelope somewhere. So if you take a left, you get stuck. So you don't doing like the complete random walk. You're doing a random walk where every time you hit the wall, you're stuck. So you can do the calculation, doesn't matter so much. But it's the style of thing that therefore I'm taking like a big range. Also, like this protein and that protein, do they have the same diffusion rate? Maybe it's not a protein, maybe it's a metabolite, and the diffusion rate might not be 10%, maybe it's 100 in those units. But all of that sits very comfortably in this big range of a factor of 1,000, so some number of milliseconds. And then we could bring us back. You remember the question we said, okay, when I was talking about the transcription, how long would it take until I'll have the response? And many people were raising all sorts of aspects related to the diffusion. Diffusion of the ribosome to this, of the signal to there, of this to that. Everything's negligible, right? Because if it's going to take you a minute to make this process, all those milliseconds, completely negligible, which is nice. It shows like this timescale separation between this process and that process, which I love.